This is a video presentation of Chapter 5, Section 6 in the 8th grade textbook entitled Dilations. Dilations are when we take and shrink and enlarge a figure. And if you recall, we've already talked about this a little bit when we talked about the concept of geometric transformations. We talked about the translation and the rotation and the reflection, and this is the one odd duck that got left out because we needed to get through ratios and proportions first, but here we are. We've now gotten through ratios and proportions, so now we can kind of wrap up a lot of the geometry stuff here by finishing off the last transformation, which is the concept of a dilation. So what is a dilation exactly? It's a transformation that changes the size but not the shape of a figure. And if you remember, the other three were grouped together because they were the exact opposite. They didn't change the size, but this one actually does change the size. It can actually make it bigger or smaller, whereas the other three made the exact same shape. It somehow got turned, twisted, rotated, whatever, but it didn't change the size. If the square had sizes that were all 2 centimeters long, afterwards they were all 2 centimeters long. In this transformation, not so. That square that has sides that are 2 centimeters long might now all be a centimeter long or 4 centimeters long. That's what a dilation does. Is it actually takes and makes the shape bigger or smaller. Think of blowing up a shape on a copy machine to make a bigger copy of something. That itself would be a dilation. The center of the dilation is the point of intersection of lines connecting each pair of corresponding vertices in a dilation. And scale factor, that's a quantity that describes how much a figure is enlarged or reduced. So if we make something go from 2 centimeters to 4 centimeters, the scale factor is 2 because it's double. If I make it go from 2 centimeters to 6 centimeters, the scale factor is 3 because it's now triple. Again, a dilation is a transformation that changes the size but not the shape of a figure. The center of the dilation is the point of intersection of lines connecting each pair of corresponding vertices in a dilation. And a scale factor is a quantity that describes how much a figure is enlarged or reduced. Alright, so let's go ahead and take a look at the first example here. It's asking me to tell whether each transformation is a dilation, and we are to explain. So let's go back and talk about some notation here quickly. Here you can see they've got these marked AB with the little marks, AD with the little marks. Remember, that indicates that that is the image, the after, what you have after you've changed the shape. The ones without the marks, those are the pre-image, or rather the before what you started with here. So what they're saying here is that on the original shape, the side marked AB is 2, and on the pre-image, the side that's marked AB goes to 6. Well, to go from 2 to 6, that means we'd be multiplying by 3. Well, because this is a dilation, everything has to change the exact same way. So that means everything has to be multiplied by 3. If everything is not multiplied by 3, it's not a true dilation. Well, when they look at side AD, that measures 2. When they look at AD in the image, that's also 6. So to go from 2 to 6, well, again, that's multiplying by 3. So since that same multiplier works all the way around, indeed here, we're going to say that this is a valid dilation. Now you might be saying to yourself, well, wait a minute, how does that really fit in with what we're talking about? I can see they wrote a ratio there, but what does that really have to do with anything? Well, realize what these really are then. These are, when they are proven to be dilations, they're really similar figures. And if you recall, that was one of the last things we did last week. The last section was about similar figures. So when we prove something is similar, which can be shown with a proportion or ratio, which is what this section is about, we prove that indeed we actually have similar figures here, which was our last topic. So again, this is really bringing all that geometry that we studied together with all those ratios and proportions that we've studied here. Notice the angles here. We didn't really talk about the angles, but the same thing has to be true here with the dilations as it was in similar figures. Whether I make the sides that make up the right angle here bigger or smaller, it's still got to be a right angle. And indeed here in that dilation, those right angles still have to be right angles. Those 73-degree angles, whether I make the sides that make up that angle bigger or smaller, still have to be 73-degree angles, right? So you still need to check the angles just like you did with similar figures. But since we see we have two, what indeed would be squares here, based on the side lengths, since we see that we have all right angles, we didn't really need to spend any time on it. But in other times, say we were talking about triangles or hexagons or whatever, make sure you do the angle check and make sure that the angles are still equal. If the angles are different, you don't even have to spend any time doing the calculation. It would not end up being a dilation. All right, number 2 is asking me to dilate the figure in example 2a on page 253 by a scale factor of 2. And then they want to know what the vertices are of the image. So what are the corner points of the after? Well, a scale factor of 2 means that everything is going to be twice as big when we're done. Now, some of these, that would be really easy to figure out. For instance, if we're looking at AC here, all right, AC goes from 2 to 5. Well, 2 to 5 means it's 3 large. And if I multiply it by a scale factor of 2, then it's going to be 6 large. But with these sides like AB and AC that cut across the coordinate grid, it's perhaps not quite as simple because they are diagonal, so their lengths, even though it might go from 2 to 4, might not necessarily be exactly that length of 2, because as you know, this would be a length of 2, for instance, but this side is actually longer because it ends up being what we know is the hypotenuse of that triangle I just sketched. So it's got to be longer than this length that is actually 2, going from 2 to 4. All right, so let me go ahead and clear off our right angle discussion here. We'll go back at this. This is pretty simple to figure out. Since they're saying scale factor of 2 here, what you can get away with, or what you can do rather, is to multiply all the vertices of the pre-image, the before, by 2, which is exactly what they're doing here. They're saying that corner A, or vertex A, is at 2, 2. So multiply each one of those by 2, and that'll give you the new vertex A. B is at 3, 4. So I'm going to multiply each of those by 2, and I find out that my image corners are at 6, 8. With C, that's at 5, 2, when I multiply each of those by 2, I'm at 10, 4. So now that I've done that multiplication by 2, I know where the corners are of my new triangle. Now it's just a matter of sketching it on the coordinate grid. End up at 4, 4, 6, 8, and 10, 4. Here's 4, 4. Here's 6, 8. Here's 10, 4. Connect the points, and there's your after. Remember, when we're talking about the sketching of the coordinates here, the first number represents the x, which is the left-right axis. The second number represents the y, which is the up-down axis. Alright, so let's wrap this up by looking at the check it out example. We're supposed to tell whether the transformation is a dilation and explain. Well, let's take the easy stuff here to start with. On the pre-image, the before, we know that the one that's got the marks on it is the after, but let's go to the before. Alright, on the before, the side down here is 1, 2, 3 units large, and here it's also 1, 2, 3 units large. When I come over here, this is 1, 2, 3, 4 units large going across, and this is 1, 2, 3, 4, 5, 6 units large. Well, as we go, look at the ones that run north-south, marked X, Y in both. That means I'm going from 3 to 6. So that means I'd be multiplying by 2. Well, in order for this to be a dilation, the exact same multiplier has to work with my other sides. Notice I'm avoiding that hypotenuse because I'm going to have to figure that out with the Pythagorean theorem. But I'm okay because look, it's 3 and 4. Well, we know if times 2 has to work, if this is 3, this has got to be 6. But this isn't 6, this is 4. So that answers the question here. Times 2? No way. All right, so no, the triangles are not similar here. The angles kind of look the same. We could have to measure them to verify to prove that this is a dilation. Indeed, we'll see, even though the right angle works, the other two are probably a little bit different. But again, check the angles here. If something is very obviously different, you can stop right away and say no. But again, in this one, because the same multiplier did not work all the way around, times 2 in this case did not work all the way around, this is not a dilation.